Well, welcome everyone. My name is Derek Prinsloo and I'm the host for today's webinar. Phil Mosher will be presenting. Phil is a field engineer in the Gulf region and is based out of Houston, Texas. Phil has been with Bentley, Nevada for 8 years and has served in the industry for 29 years. We are recording today's session in an effort to make these videos available to you and your colleagues at a later date. We ask that you make sure that you are on mute and refrain from broadcasting your video, please. We are using the Slido app for questions today. As a default, your questions are made anonymously. I always recommend voting on your own question as it kind of gives it an extra bump up in priority. But by the same token, please vote on other questions that you find interesting. As we are recording the session, we'll wait until the very end of the presentation section. We'll stop the recording and then we'll work on the questions and the Q&A at that time. Just as a reminder, to get to the Slido app, you can either download the app on your phone, or you can go to the website as listed here on the front page, sli.do, and the code to join is MDS. That code is going to be on every slide going forward in case you forget it right now. But without any further ado, I'll hand it over to Phil. Get going.
Okay, well, thank you, Derek, and welcome everyone. This is the afternoon session of What Can MDS Do for You? So I'll start by giving you a brief description of our MDS organization, and then we'll get right into what we do and how that can benefit you. So as a company, Bentley, Nevada manufactures protection and monitoring solutions. And as a service organization, we support those solutions with over 500 employees worldwide. And you can see from the map, we're well distributed across the globe. Most of our organization includes people that help with installing and retrofitting both our hardware and software solutions, and those that help maintain and support those solutions, both hardware and software. We have many people involved in our internal training programs related to service. And in the middle here, we discuss machinery diagnostics, advisory services, and analytics, and that's where the MDS group fits in. So MDS is a subset of our service organization and stands for Machinery Diagnostic Services. This group was started back in the 1970s and has grown to over 160 engineers worldwide. And so similar to our prior service group plot, you can see that we're all over the globe. We've got a concentration here in North America and another one in Europe, but again, we're spread out. And the general idea is that if you need one of us, we're not too far away, maybe a few hours driving or 1 or 2 flights, and maybe just a remote session away, depending on the circumstances. So within our organization, we've got an internal certification program with 3 levels. And you can see the distribution. And these 3 levels involve internal training, internal certification, experience, kind of a display of our experience. And as we go up higher levels, it gets more into the teaching and presenting, writing papers. And also many members of our group have ISO category 2, 3, or 4 certification. And so you can see that distribution as well. Okay, let's get right into what we do. The way these topics are laid out, the left-hand column, rotating machinery diagnostics, startup turnaround assistance, system 1 audit, and rotor balancing. These are tasks that we do all the time, and all of our MDS engineers are trained and proficient in these tasks. We spend a lot of time troubleshooting machinery and also helping you check your system to make sure that it's collecting all the information so you can troubleshoot also. The middle and the right columns, these are more specialized tasks. And I don't know if we have any single individuals that are experts in all these tasks, but definitely across our organization, we have experts in each of these areas. And so we've got a large variety of background of engineers. Some have come from OEM repair shops, Some have come from plants, refinery, power plant, petrochemical, and others are fresh out of school and straight into our internal training programs. So moving to the first item, and probably covers most of the topics we're going to discuss, is rotating machinery diagnostics. Many of the items we're going to discuss fall under this category, but this involves troubleshooting of rotating machines. If we come on a one-time basis to look at an event, maybe there's been an issue with the machine, we come and analyze the data, or we come collect data and look at that, we call that a reactive job, a single event. But more and more we're doing contracts or supporting service agreements, and that's where we have an agreement to come on a routine basis, commonly every 3 months, but maybe monthly, maybe every 6 months or annually. And these contracts generally go from 1 to 5 years. And we take a look at the machinery, definitely diagnose what's happening, but maybe also proactively look ahead and see if there's issues that we can make you aware of. We look at all sorts of equipment. As Derek said, I'm based in the Gulf Coast, so I see a lot of turbine generator sets, gas turbines and steam turbines, but also in the refineries and petrochemical, we see a large number of compressors, typically motor-driven with gearboxes. But basically, I think we look at almost anything that rotates and vibrates. We look at all different OEMs. So hopefully I didn't leave anybody out with this list, but this is a summary of what I'm used to seeing. So when we come on site to look at equipment, we generally bring our Audit 408. That's a 24-channel data collector. We can convert it to 32 channels if necessary, but this is probably the most common thing we use. And we connect it to a 3500 rack or maybe a controller. Sometimes we bring our own probes, temporary probes, and instrument the machine and connect that out in the field. So many different ways to gather the data. If System 1 has been installed on site, definitely we can look at that, and also remotely we can, if that's possible to get in, we can look at data that way. We also do quite a bit of balanced plant work, and so we have our handheld data collectors. We use that for balance of plant work, and also even on large turbo machinery. Even if we have our Audit hooked up, we may want to take a snapshot of bearing cap vibration, LP exhaust hood, generator feet, foundation, any kind of structural issues. So however we do it, we can collect all the vibration data, analyze that, and we try to correlate that with other data, typically bearing metal temperatures, process data, load data, whatever's relevant to the machine we're looking at. And also we consult with the plant personnel, again, to find out what's happening, what's been the history, generally talk to operators or reliability engineers familiar with the equipment. Many of the turnarounds were there, and the crew is still there, so maybe the millwrights and the supervisors, we can find out what work was done, what potential issues there were. So we try to take all of that information, and in the end, the final deliverable on a project is the report. And depending on timing, this could be 1 to 2 page exit report, or it could be a full-blown formal summary. And that's kind of depends on what's requested and what's required, but we analyze all the data, present all our findings and conclusions, but the main point we try to get to, like if this is a balancing job, we document all that. But if we're not there for the balancing work, we would definitely give you actionable recommendations. What do you need to do? Is this something urgent that needs to happen right away, or can this maybe wait to the next outage? We get asked a lot, how long can the machine run this way? We generally can't answer that directly, but we can give you an idea of the severity, if it's immediate or not, or maybe there's certain parameters that need to be watched closely. And if those change, then we need to reevaluate. But in the end, the goal is to give you something to work with. If you need to balance, what weights do you need? Where do they go? do you possibly need to come down and check alignment or open up some bearings and check liners? And again, this is done in conjunction with the other experts at the plant also. One of the main things I get involved with, probably the biggest percentage of our workload, is startup and turnaround assistance. And there's two halves to that. There's before the outage and there's after the outage. So I want to spend a little time on pre-outage baseline collection. It's always good to get a good data set before you go into an outage. That way you can compare before and after. And generally, I like to look at full load and partial load conditions if possible. But many times when we're on a regular job, or we're just looking at steady state data, a lot of times we'll ask, can we shut the machine down and start it up again? Many times we see rolling eyes and we get told that's way too expensive or we can't bring the plant down, which we understand, but it's very valuable to get that shut down and startup data. And so one of the perfect times to get it is when you have to shut down anyway for a turnaround. And the reason we want to look at that data is a few things. One, it's nice, I've shown some Bode plots here, but we like to watch the shutdown and see the critical speeds. If we have historical data, maybe we can compare to see if that's changed or not, or if the levels are excessive. And we like to see that slow roll data. I've got an example here of an orbit. This is actually at full speed, and you can see the orbit's pretty small, but the scratches make the signal a lot larger than it should be. And so these are nice things to find ahead of time, because maybe if you're pulling that rotor out, you could address that. You could burnish those probe targets and make that issue go away. So some of the things we can find out, as simple as faulty transducers, like in this case, if your transducer's moving around a lot when the machine's on and off, that's a good sign. Maybe it's as simple as the XY probe sets are swapped. And, if you're just looking at overall conditions, that's not a big deal. But if you think you're going to need to balance, then you really need to know that you're looking at the right probe in the set. Again, maybe you can, during the outage, burnish the surface. But also we can find things like maybe we're seeing excessive preload or unloaded bearings, both of which would point towards doing an alignment check. Maybe we have indications of enlarged bearing clearances, excessive imbalance. So these are the kind of things that are good to know going into an outage, because we can find all this out later on the startup, but it's nice if you can address these issues during the outage. And so the other half is the post-outage startup. And again, same concept. We watch the machine start up. Generally like to watch it through base load steady state, and maybe see key partial load conditions depending on the machine type. And again, we're able to watch the slow roll. We're able to see it go through the critical speeds. If we think down the road maybe balancing is going to be required, it's nice to see how many criticals it goes through, and kind of gives us an idea of what mode we're dealing with and where weights may need to go if we need to use it. But on large turbo machines specifically, a lot of the problems you see show up at 1 times running speed. So imbalance, seals rubbing, misalignment, that can all show up at 1x. And I know sometimes people are used to finding misalignment at 2x, but on large sleeve bearings, sometimes you can just see an orbit that's kind of squashed, but not so much. You're seeing the 2x, and you see that the shaft center line travel as the machine starts. Maybe it veers off one way or the other. And so seeing the full startup and the base load and having a comparison to what it looked like when it shut down, that really helps trying to parse out the difference between all these different issues. And of course, there's different remedies to these, so it's nice to figure out which one we're dealing with. If it's imbalance, may need to start a balance program. If it's just rubbing, may just need to shut down, slow roll for 4 hours and try it again. So also we can see the simple things like maybe transducer issues. One that's probably more exciting for us than it would be for you is occasionally we see instabilities. This startup plot, all of a sudden there was a spike at a subsynchronous vibration. Turned out the bearing was unloaded and we had an oil whip phenomenon. So anyway, those are the kind of things you can find if you're there watching the startup, and then of course in the end recommending solutions to what we see. Now, many times after a startup, usually this is when we get into this, we get involved in rotor balancing. Generally, field balancing is what we support. And I mentioned shop rotor balancing. I don't mean that we have a shop to do balancing, but more sometimes we go to shop tests, and in the process of that, we help balance a unit. We can get away with single plane. That's always nice, but many times we get into multi-plane balancing. We've got some really good tools to do that. I think one of the strengths of our organization is we've got engineers all over the world, and we've seen, as a group, many types of machines. So if I end up on a job with something I'm not that familiar with, a machine I've never balanced, I can most likely find a coworker that has information, maybe even data on a similar machine that we can use. So that's kind of a benefit of being part of a group that does this a lot. Generally, we're doing this on site, but more and more with remote connections and System 1, we can at least make their recommendations that way if we have sufficient data. So the goal of rotor balancing is, we'd like to always do it in one shot, but that's not always possible, but we strive for the best first trial shot. There's a lot of things that go into the rotor balancing. I do get asked a lot if we have a calculator we plug the numbers into and get the answer. I wish it were that easy. We do have some good calculators, but really very dependent on what you put in it. So, with each rotor, here's just a simple model of a symmetric rotor. And as you go up through the first critical, you'd have something similar to this, and you'd be in phase end to end. You get into the second mode, you'd be out of phase, and then back in phase in the third mode. Generally, we're working on the end planes, but occasionally on some machines we can get a mid-plane shot in. But we need to look at various load conditions. Does this help full speed, full load, and full speed partial load? Is it good through the critical, or maybe it's high through one of them? And at least in my area, many of the machines I look at, it's a turbine generator set. 3 rotors, 3 cases, and we're rigidly coupled. So what happens on this end of the unit can affect this end of the unit. Run into situations where the generator rotor was pulled. That's the only work they did, rewound it, but when they put it back in, we had high LP vibration. So on these rigid rotors, everything seems to affect everything. And balancing ends up being maybe half art and half science. But again, the good thing is within our organization, we've got a lot of experience. We've got a lot of empirical data. If we don't have prior data on a specific unit, we probably have some on a similar unit. And that all goes to getting the first shot as good as we can get it. Sometimes that's low enough, or other times, at least if it's not low enough, we hope it's enough of an effect that we can calculate a good next shot. So switching gears a bit now, condition monitoring system audit. Many of our customers have System 1 installed. And on the left, that's a snapshot of System 1 Classic. On the right, that's System 1 Evo, which we introduced it as that. Now we just call that System 1. So that on the right, that's System 1. This is System 1 Classic. And our main goal when we come in to do an audit is to treat the information like what we would need if we came on the site to do a diagnosis. Is the system set up to give you everything you need? You don't want to have some sort of failure or major event and go back and find out you don't have the data that would help you analyze that. So we look at things such as the data collection rates, the frequency spans in question. We generally go through all the plots, make sure they're all working, but then make sure the resolutions are correct, like on startup and shutdown. Do we have enough data to make good determinations if something's happening? And so this happens a lot on our supporting service agreements, where we come in on a routine basis. And usually in conjunction with this, we do machine health audits, machine condition audits, which goes back to what we've already discussed. We take a look at the data and see if we see things that could be pending issues for you down the road. So now we'll get into some of the more specialized tasks, reciprocating machinery diagnostics. So with our 3500 monitors, we have a solution that's a combination of some special cards for the rack, and in conjunction with System 1, we're able to take the information and look at it in a certain format that makes it suitable for diagnosing recips. We look at both mechanical and performance related issues. Generally, we use, if we can, we use some sort of multi-event wheel, so we can get multiple indications during one revolution, and try to build as accurate as we can plots of things versus crank angle. So if the piston goes from the head end to the crank end back to the head end, we call that 360 degrees, and we have samples every half degree. And so we look at things like frame vibration, crosshead acceleration, chamber pressures, and piston rod position. And this is just an example of some of the plots, but we look at the timing. Again, this is crank angle. We look at the loads, load reversals to see if there's proper lubrication at the crosshead pin. Do we have indications of valve noise, or maybe something mechanical like a loose nut on piston? And also, we just look at the cycle on each end of the chamber, each chamber on each end of the piston, to see if that indicates packing leaks, leaking valves. And then rod position, we kind of promote that over rod drop, although we can look at both. But basically, that's having a horizontal and vertical probe setup on the piston rod, and we look at the path of that, and we track that over time. So that can be a good indication of wear ring diminishing. Now, we do offer a number of training classes that are related to vibration and machinery diagnostics. All the ones I'm familiar with, the teachers, the instructors are all either current field engineers or technical leads that came from the field engineering group. So these classes are all very practical. They're as much workshops, applied workshops, as they are theoretical presentations. So it's a good mix. And starting at the beginning, we have a short fundamentals of vibration class. System 1 for turbo machinery, that's a 3-day class. That focuses more on using System 1 to monitor your equipment. But I think the flagship of our training program has always been our machinery diagnostics course. And this is a 5-day course. The fundamentals of rotating machinery. And again, it's a good mix of theory with applied workshops. And it goes through all the basics of monitoring large turbo machinery, generally focusing more on the sleeve bearing type machines. Sleeve and tilt pad. We've got a special class for recips, 3-day class. Goes through everything about the way our plots work and the instrumentation, identifying malfunctions. Applied diagnostics, that's a real good class after the basic machinery diagnostics that really focuses on actual case histories and taking all the plots that you learn about in the first class and applying that. So again, very, very practical class. And in the basic machinery diagnostics, we do touch on single plane, multi-plane balancing, but we do have an advanced field balancing, which really gets into the specifics of not just the theory and how you handle the different mode shapes, but actually how you approach a real machine, how you locate the key phaser, find your references, make sure you're putting the weights in the right end on each end, So very practical class. And finally, Advanced Machinery Dynamics. This is a very good 3 to 5 day course. And it just kind of proceeds on from the other classes, gets more into rotor modeling, bearing design, and very specific machine failures and how to diagnose those. So all these, again, led by experienced field engineers. And if you want more information, you can go to this website, bentleytraining.com. And most of these are, well, they're all offered in our training centers. Some of these we do come on site to offer those, and we're starting to do some of these remotely now. So if you go to the website, you can find more information about that. So continuing on with some of the specialized tasks, one of those is Rotordynamics modeling. We have the we use the software from Texas A&M called XLTRC2. It's an Excel interface, and basically with rotordynamic modeling, you're building a model of the shaft, and maybe you can do some testing to do ring testing to make sure your model is good, and then you add in the bearings and the seals and try to build up a model of what the machine's actually going to do in operating conditions. This is always done on new machines, and it's frequently done if there's a retrofit of a machine. Certain requirements, under API for how to do this and when it's appropriate. But that's something, it's always good if we can find this rotordynamic model on machines we're working on. And we do have individuals that like to work on these models. Structural vibration. We have licenses with ME Scope. So we have the ability to do impact testing, developing mode shapes, or we can instrument a machine with numerous transducers or using one transducer and taking multiple readings. But build a model in ME Scope and then watch and see what the vibration levels look like. As the machine runs, it kind of gives you a 3D effect and helps you isolate maybe what you need to focus on, what's moving too much. And we'll spend a little time on this later on motion amplification, special case of this using a camera. And we've got some neat slides on that. Magnetic bearings. We do have some applications to monitor magnetic bearings. Personally, I've not been involved in this, and I don't have a whole lot to say about it, but we do have individuals experienced in this. Okay, so motion amplification. If you're not familiar with that, that's a camera with some specialized software where you can set it up and view a machine, and basically if you get it set up correctly where you have a good reference and your camera's not moving, you can watch the machine as it's operating, and you amplify the motion. So what I'm about to show you, I'll run this. It's not shaking that much, but it allows you to amplify it and see the areas where you may have an issue. So in this case, this is a aeroderivative gas turbine. Had some issues with the seismic transducer connection that was continually having issues. It was wearing over time, and that would cause intermittent spikes, which would trip the machine. So give me 1 second. I will pull up the file. Okay. And so this is where those connections were made, this little patch panel, and you can see, again, it's not really shaking this much. If it was, that would be easy to see when you walk out to the unit. But again, these cameras let us quickly set up, relatively quickly compared to doing a full ODS on this unit, and we can see where the motion is. It's apparent that there is a lot of motion here where this connection is vibrating, and so maybe something can be done to remedy that. And my coworker sent me these 2 slides. Another example he had was, this is the generator drive end right next to a test cell, and mostly what they were testing was over on the right hand side, but you notice that they had significant motion here. And so let me this? Okay, there we go. So again, not really moving this much, but it's neat to see. You can see the magnified motion here, obviously moving all the dials, but also you can see the end wall of the generator, how that's flexing in and out. So the hope was they could address this vibration here and reduce everything that you're seeing. So it's a neat tool, and it's relatively quick to set up compared to doing an ODS with multiple transducers and building a model. Torsional measurements. Torsional vibration is sometimes called the silent killer because it's not something people normally look out for. It's not something that always will show up in radial or axial vibration, which is what we're typically monitoring. But if we do want to look into it, just with our standard Audit and a key phaser signal, we can look at torsional frequencies less than half the shaft speed. If we need to go beyond that, we could take a little work, but if you use zebra tape or maybe a timing wheel, something to give you multiple events per revolution, you can expand the frequency range that you can analyze. There is a specific torque meter. The torque meter is not a Bentley product, but we do have a special card for our rack that we can monitor this if this coupling is in there, and we can analyze torque that way. Something new and exciting, I think it's still under development, but we have a transducer that's currently being tested at GE Power in France, and this is more of a probe mounted radially like you would a Prox probe, but you're able to monitor torsional frequencies with that. So again, that's under development, but I hear that it should be available sometime soon. Okay, so that's the discussion of everything we do. I threw in a few case histories here just to give you some examples of things that we found before. In this first one, we have a gas turbine trip due to high vibration after startup on the generator. And so we've got a waterfall plot here. I realize it's a little small, but as it was running, all of a sudden I had subsynchronous vibration. And this latched on to the first critical of the rotor, and so that's what we call oil whip. And you can see the magnitudes jumped up quickly and much higher than the regular 1x vibration. So that caused the unit to trip. And what they found out was they weren't properly heating the oil prior to startup. And so the MDS engineer was able to work with the plant personnel, and they kind of figured out what was causing this. And so they were able to change it where the system didn't start until they had appropriate oil temperatures. And doing that, this phenomenon did not occur again. And they estimated conservatively, they say 60K savings. So case history, this is one I got to be involved in. So it's gas turbine. After an outage, had high vibration. So the customer asked us to come in and take a look. And on one end of the unit, having high vibration, not only during startup, but also as they loaded, the vibration went higher. And so with balancing, we don't always have access to everything we want, or not always able to get into the machine we want. So in this case, that was going to be difficult, but we did have a balance plane on the coupling here, on the accessory coupling. And so we were able to put, as a trial weight, we put two weights, two washers here. And that was, we moved the vibration, but we were able to calculate final solution. And so this is the final solution, able to put weights on the coupling. Again, these are just washers that we added here. And the result was the vibration came down by 4.7 mils. So from there to there, and that's always a good feeling as an engineer to leave the plant with a lower vibration than when you started. And this final case, this is one I was involved in also. A steam turbine on startup kept spiking on bearing 2X. going into alert, so it wasn't tripping the unit, but they didn't like having this on their panel every startup, and they weren't sure why it was there. So this is a 60 hertz machine going up to 3600 RPM. But every time they went through 2400 CPM, they had the spike just on this probe. So I was there during the outage where they had the machine torn apart, and got a chance to kind of go through everything they had on the ground there. And the stinger assembly for the bearing 2X was longer than all the other probes. You can see this was the 2Y, it's kind of a short pipe mount here, but the 2X was longer, and that was to accommodate this longer stinger. And never really had a good answer about why that one was longer, but did have a chance, had an impact hammer with me, and so I was able to ring the different components and realize we had a resonance there right at that same frequency. So the recommendation was shorten that pipe stem and replace this transducer with something identical to the rest. Now, unfortunately, this is blank because on many cases, I don't know if they made the fix, but we never got a call back. Things ran good after we left, so I think this is pretty common that we don't get to see the results, but it seemed pretty obvious from what we had seen that was it. So hopefully that worked out for them. And so that is all the slides. And Derek, we can get to the questions now.